That was easy.
Hi, so I want to talk about one of the most important theorems in logarithmic complexity, but in order to build up to that, we need to first talk about NL completeness. So this is like NP completeness, but for logarithmic space. So remember, NL means non-deterministic log space. And we talked about this before. You can't really have logarithmic space when the input itself is linear in space. It's logarithmic additional space. So what does NL completeness mean? So the definition is almost the same as NP completeness, but with NL instead. So we have NL complete if the language is in NL. Well, you got to be complete for the class. You got to be in the class. And every B in NL, so every language B also in non-deterministic log space, log reduces to A. What does log reduces mean? So that means that the Turing machine that does the reduction itself from the one problem to the other problem only uses log n workspace to do the reduction. It's not log n total space because that's impossible in general, but it uses log n workspace. So remember that the Turing machines that we've been dealing with have an input tape, they have a work tape, and an output tape. We largely ignored the output tape when defining NL, but for NL completeness it's necessary because what happens on the work tape is all the work that we got to do, and on the output tape we can never move left, so whatever we put on the output tape is there forever. So in order to do the reduction, what happens is that the thing that starts off with some input in B is going to start doing the reduction, and it's going to start putting stuff on this work tape, and it's going to do its work, but it can only do log n amount of space. And on the output tape, whenever the B machine is done, so let's try to visualize this a little bit better. So we got the three tapes here, and this is going to be the reduction machine. So it's gotten some input right here, it's going to do some work right here, and of course we can only use at most log n space here. The input, we can never modify it, so that doesn't matter. Here we can only do log n space, and this is the output. And then when the A machine takes over, or the conversion is done, then the input tape to the A machine is going to be this. So effectively the A machine is going to ignore these two tapes right here. This is the only one that matters. And we can never move left on this tape. We can only put stuff and move. Okay, so I want to prove one important thing about these log reductions. So let's suppose that we have a language B that's in deterministic log space, not necessarily non-deterministic, but in log space. And let's assume that some other language A log reduces to this guy, then we can conclude that the earlier one is also in log space. And you may think, okay, this is reasonable to do. So let's think about what will happen. So we have the reduction machine doing its work right here. So let's say we got our three tapes right here. And then what happens is that we got some output down here. And of course, when the when the reduction is done, this third tape is going to be the input tape to this guy right here, obviously. So let's think about what is the possible issue with this. Well, let's suppose that this output for some input W, let's call it f of W, where f is the actual reduction here. But here's the actual problem. So we know by assumption that B is in log space, and what we want to show is that A is in log space. So let's think about what this f of W is. Remember that the output tape is not limited in how much you can write on here. The only thing that counts against us is the work tape. So let's assume that the reduction is done, and let's say that this f of W is, or at least the size of it, is big omega of log squared n. So you may think, what is this? So omega just means at least. It's like big O, but at least instead of at most. And log squared n is where n is the input size. Remember, the output can be arbitrarily big as you want. So when the B machine takes over, it might use log of this, but it's not limited in that amount of space. So let's say that we use even more than this. Let's say that we use, oh, I don't know, 2 to the n. So if n is the size of the input here, the output could be arbitrarily big. That you can use as much as you want. Well, let's suppose that the B algorithm now takes over. So the B algorithm, which runs in logarithmic space of its input. So its input is this size, and if we take log of this, it's going to be linear in n. And so that is way too much space for the A machine, which we're trying to show that runs in L. So how can we actually do the log reduction, make sure that this thing could use a lot of space? We have no limitation on how much space it'll actually produce, but we still want to make sure that A in total uses only a logarithmic amount of space. The trick, as we're going to do next, is to do the reduction over and over and over and over, only giving a little bit of information each time. This B machine is going to start using some symbols of this. So maybe let's say that the B machine is right there in the computation. Then what the A machine is going to do is whenever the B machine is asking, okay, I want the next thing in this computation right here, I want the next guy. Then what the A machine is going to do is going to rerun from scratch every single thing in its computation. Why does that guarantee that we only have a logarithmic amount of space? It's because A is restarting over and over and over. The output is not limited at all. And so the B machine is only accessing one symbol at each point. So maybe, for instance, this pointer can move backward, for instance, but the A machine is just going to rerun from scratch every single time the B machine wants another bit of the output up until it produces this value. Rerun from scratch every single time and keep track of where everything is. It turns out that because the reduction itself only takes a logarithmic amount of space, and the B machine is only accessing one bit at each time, it's not keeping everything to itself every single time, then because of that, we are guaranteed that we only use a logarithmic space in total, because the log reduction only takes log space, and the produced output, it could be as big as you want, but we're rerunning it every single time. So the B machine only has access to one bit every single time, and we keep track of where the B machine is, but by assumption, the B machine runs in log space. And so therefore, those two are just adding on to each other, and we have a total, maybe a big constant times log n in total for A. And so therefore, that will tell us that if we have any language that is NL complete, then if that NL complete language is in deterministic log space, then that will imply that L is equal to NL. Because if that language is in L, say like this one, then that means that every language in NL log reduces to this guy because it's NL complete. But if it's the case that it's in L, then that means every language in non-deterministic log space is in deterministic log space, which is pretty dang cool. All right, let's prove that the directed path problem is NL complete. So by the definition of NL completeness, we need to show that it runs in non-deterministic log space and it is NL hard, which means that every language that is in NL reduces to directed path. We've shown in the last video that directed path is in NL because you only need to keep track of the current vertex you're at and non-deterministically guess what the next vertex is. How do we show that this is NL hard? That means that we got to take any language that is in non-deterministic log space and log reduce it to directed path. So let's pick some language A in NL, and we want to show that A log reduces, and I'm going to use this notation, to D path. And all that we know at this point is that A runs in non-deterministic log space. We have no idea about what it is otherwise. So let's assume that there's some non-deterministic Turing machine, I'm going to call it M, that runs in non-deterministic log space and decides A. So let's say that M is a non-deterministic Turing machine, and we want to accept a particular string W if and only if the graph that we produce has an ST directed path, I should say. And so how is this going to work? The only information that we have is that M is a non-deterministic Turing machine and it runs in log space. So how can we actually use that information to construct a graph? It's not even related to the Turing machine whatsoever. The key to note is that the output tape is not limited at all. The work tape is limited, definitely, but the output tape is not limited. So the graph, let's represent the graph as an edge list, and that's where the importance of different representations of graph actually matter. So here, let's represent the graph as an edge list, which we can do without loss of generality. Directed edges in this case. So what are the edges going to look like? So let's say that we have some vertex x and it has some edge to y. Well, the only thing that we have available to us is this non-deterministic Turing machine. So all that we're going to do is that these vertices right here are going to represent configurations of the Turing machine. So x and y are configs of the Turing machine. And maybe I should use a different color than yellow for this. Let's use blue. So these are configurations of this Turing machine. And there's a directed edge from x to y if and only if we apply a transition from x, then we can get y. It could be one of the choices because M is a non-deterministic Turing machine. But as long as there's a choice to get from x to y, I'm going to make that edge there. And remember that we have to provide these s and t vertices, that there's a way to get from s to t. And in this case, we're going to have s be the starting config. There's always exactly one, which is the start state followed by the input here. And the unique accepting config, we're going to modify the Turing machine so that no matter what, because it's a non-deterministic Turing machine, whatever accepting config that it is, we're going to have a bunch of directed edges going to some vertex t right here. So if there was a whole bunch of places we could have ended up as an accepting config, we'll have a way to get to t because they all point to t. And so now this graph here has an st directed path if and only if m accepts w. Because if m accepts w, then there's a sequence of configs, a set of choices that you can make in order to get from start to the accepting one. Well, that corresponds to getting from s to t because we're only making directed edges exactly when you can apply a transition in the first place. And if m does not accept w, that implies that there's no way to get from s to t. And therefore, we have shown that this is a valid reduction. However, what we need to show is that this reduction takes logarithmic space. So remember that this non-deterministic Turing machine runs in logarithmic space, and I'm going to call it c times log n in this case. So what we need to do is that we don't know necessarily what the computation is going to look like in the non-deterministic Turing machine. So what we're going to do is we're going to list every single possible computation that could ever occur, including every single configuration that could occur. So I have no idea what this Turing machine is going to do, and there's no limit to how big the graph that we're going to construct is because the output tape is not limited, only the work tape is limited. So what we're going to do is we're going to look through every single configuration of at most c times log n in size, make a vertex for it, and we're going to make a directed edge between every single pair if one can yield the other one. So how do you actually verify that one can actually yield the other one? So let's think about what that would entail. So if we have a tape here, so this is totally a separate thought. So it's not like the work tape or something, although it is in this case. So let's suppose that we have a configuration C1 right there and another configuration C2. How do we verify that one can actually yield the other one? Well, the only difference is where the tape head is. So the only thing that we need to do is to make sure that everything else in the configurations is exactly the same except around where the tape head is. And that can be done in log space because each one of these is log in size, or at most log in size. And doing the whole zigzag trick of marking something and going back and forth, that will take a log additional factor, but that's fine. It's just additive to the log n, not multiplicative. Okay, so we're ready to state our main result, which is due to Immerman-Szelepcsényi. And yes, that is how you pronounce it, Szelepcsényi. I've looked it up, that's how you pronounce it. So they showed that the complement of the directed path problem, which is d-path complement here, is in NL. We saw that the original problem is NL complete, and if we show that this guy is in NL, that would imply that NL is equal to coNL. So coNL is just the set of languages whose complements are in NL. And we do not know whether this is true about time. So we don't know whether NP is equal to coNP. So in order to prove that this is actually true, we need to really use the fact that we are working with a small amount of space. They actually prove something much more complicated, which is that if we look at n space of some function f of n, then that is equal to coN space of the same runtime. So non-deterministic space classes are closed under complement. So let's get into how you would actually prove that dpath complement is in NL. Okay, so we have two vertices in our graph right here, S and T, and what we want to determine is whether or not there exists a path, and we want to figure out when there isn't a path. So one thing that you can obviously do is just run Dijkstra's algorithm, for example. Just run Dijkstra's algorithm from S, see if you ever hit T, or you can run breadth first or modified depth first, lots of different approaches. The problem with them is that they take a linear amount of space no matter what you do, because you have to store the frontier of vertices as you go. So how would you actually determine whether or not there does not exist a path? Because it seems like there's so many different possibilities in here of like where we can actually go to reach T or potentially not reach T. So here's the key. Their theorem says if there is a path from S to T, then there is a path from S to some node that reaches T. So, and that's not too surprising. So let's draw a little bubble right here, or cloud. And so if we can reach, let's say, some node right there, and that has some edge that goes to T, and we can reach from S to that guy, then clearly we can reach T, and then we should reject in that case. So how would we verify that we can actually go from here to here? The key idea of Immerman-Szelepcsényi was to observe the graph in onion layers, and that's my term, so onion layers. How does that work? Well, what we're going to do is we're going to look at vertices one node away and figure out how many there are, how many nodes there are. And then what we'll do from then on is we'll go to 2 layers out, see how many there are, and then go to 3 layers out, etc., etc., etc. And if there is a path from S to T, then it can't be more than the number of nodes, obviously. So in order to get from S to T, we must take at most the number of nodes, number of edges. You can even make it n-1, but that's not the point. So why is it important that we actually calculate the number of vertices in each of these little onion layers or cloud layers as we go? The key idea is that we're never storing the actual path. So the only information that we can keep around is how many vertices are at each layer. Why would that be helpful for us? So suppose that there's some node like right here, and it goes out to 1 layer away from S, further away. Why is the number important? So when we explore up to this particular level right here, we verify that we have seen the correct number of nodes at that layer, and then we calculate the number of nodes at this layer right here. And then when we go to the layer after that, we keep around the first yellow layer as a count that we had and restart the computation from scratch, from S, and then go that far out, let's just say 2 layers out, and I'm going to determine the number of nodes at that distance. I've kept the counter already, so if the choices that we make here have a different count, then we should reject because the count wasn't determined correctly. So that is helpful for us in order to verify that we have the right number of nodes. The thing is that in order to reach T, we could visit some weird vertex way over here, right? So the thing is, in order to determine the number of nodes in here, we need to, in principle, consider every single node of the graph, because in principle, some node right here at 1 layer could be connected to everything else in the entire graph. So that's how their algorithm works. So let's look at it in a little bit more detail. Okay, I just wrote the entire algorithm out. It's actually really complicated, but I'm going to get you through it. If you want to check all the details, I invite you to do so, but I have omitted some of the details just for sake of clarity. So remember that we're trying to figure out whether the directed path problem is in non-deterministic log space. So we're given this graph G, we're given the graph G, a vertex S, and another vertex T, and we want to verify whether or not there is a path from S to T and accept exactly when S does not have a path to T. Notice that we're talking about the complement here, so it could have malinformed inputs. We're eventually going to accept if the input is malinformed anyway, so it's not a big deal. But just worry about when S is not going to connect to T. So what we're going to do, as in the idea, is we're going to determine the number of nodes at distance I from the start node S. And then what we'll do is verify in increments whether the count was made correctly. Okay, so then how's this going to work? So notice that any path from any vertex to any other vertex must take at most the number of nodes minus 1 in any graph. So I'm having a loop that starts at 0 and going to m minus 1, where m is the number of nodes in this graph. We can do that in log space because I can just have a little pointer that points at the node that I'm currently looking at, and that only takes log space to store that one pointer. Okay, so then what I'm going to have here is I want to determine the number of nodes a distance I plus 1 from S. And I'm going to initially start it at 1, and as we're going out, so notice that this is going to be I plus 1 or less. So this distance I is distance I or less. So how's this going to work? So I'm going to start it at 1. Notice that S is distance 0 from itself, so that's going to be included. I'm including it in the sense that I'm incrementing a counter. I'm not actually storing the vertex here in order to save space. So what I'm going to do is I'm going to look at every single other node in the graph. And what I'm going to do is determine the number of nodes, one away from any node that's I plus 1 away. So in the idea, we had S right here, let's say, and I'm going to look at every single vertex that is a distance I away, as well as include the ones that are a distance I plus 1 away. So what this D counter is going to do is determine whether we have the correct number of nodes in this region right here, in the white region. So the D counter is going to handle the white region. And then from the white region, we're going to calculate the number of nodes that we can see in the green region. And so in the next iteration above that, we're going to figure out whether this green count was done correctly, and then calculate the next level up, and then the next iteration is going to march in lockstep all the way to the very top here. So how's this counter going to work? So we're going to choose non-deterministically I vertices from S because I want to figure out all the things that are a distance I away or less. So there was actually some for loop that I forgot to write down, of course. So this U vertex, I want to see if I can get to V, which is on the green line. So I want to count how many things are on the green line. So let's call that V. And I'm looking at any vertex that could potentially appear on the white circle. So let's say that the U vertex, which I want to see if it's on the white circle, and if it can actually reach V in one edge right here, one directed edge. So what I'm going to do is I'm going to move I vertices from S non-deterministically, and if I can't reach U, I'm going to reject. But the good thing about that is, if I can't get to U in I steps, then I'm just going to skip it non-deterministically. So this choice right here is purely non-deterministic. Once we found U, which is getting to this second bullet point right here, then that means that we found U, and so I can increment the number of nodes I see on this white circle. And we're going through all the nodes here, so I'm going to calculate some number there, and I'm going to increment D. D is the number for the white circle. And if it's the case that U has a directed edge directly to V, as in this picture, then that means V is one of the nodes that is a distance I plus 1 or less, because this V could be on the inside closer to S. We're going to go over every single one of those vertices away from S. So any other vertex that's not S, I'm going to increment that number. So now I know the number of nodes within the green circle, which is including all the ones in the white circle. So then now I'm keeping track of how many vertices I can reach at all in a particular distance. So then now at the very end, I keep doing this over and over and over until I have explored as far as I possibly can go in principle. Because the farthest path from any node is going to be m-1 or less. We're going to make some additional count here. So if the count we just determined right now is different than the previous count that we explored earlier, then we will reject. So in principle, we are keeping track of the exact number of vertices I can reach within I or fewer steps. I have I plus 1 here because we have m-1 here, and it's just a good measure. So here, now at Cm, I have determined the number of nodes I can reach within m steps or fewer. And so now I just do the exact same thing as this, but I work with m edges away from s, and if I reach t ever, then I'm just going to reject immediately. And if the number that is found is not exactly that number, so if the number that is found is not Cm, I enforce that we reject. Why this? Because I want to make so that the non-deterministic machine is forced to make choices. If we didn't have this, then we could just go down to the accept thing and then immediately accept, which is not what we want to do. We want to actually verify this. So what's happening here is we are forced to keep track of the number of vertices that we can see at most m edges away from s. If the number is not this particular number, then we reject. And so therefore, we must have explored as far as we possibly can go. And so therefore, we will have shown that s is not connected to t if we hit this step. If s is connected to t, we must hit this step, because in order to even get to this, we must have verified the number of vertices that we can see, which is in principle exploring the whole graph. And so that's the Immerman-Szelepcsényi Theorem, which says that NL is equal to coNL, and more precisely, that non-deterministic space classes are closed under complement. So hopefully that was interesting. Leave thoughts about NL versus coNL and complexity theory into the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.
That was easy. That was easy. That was easy.